dear students. So, we will continue our discussion on electron plasma wave. So, we have derived this set of equations earlier 1, 2 and 3, which are the governing equations, and we have defined the perturbed variables as equation number 5, and the conditions which govern the plasma motion are given in equation number 6. Now, we have to substitute equation numbers 5 and 6 in equations 1, 2 and 3. The purpose is to linearize the governing equations. So, we will take the continuity equation first. So, we can write dou by dou t, the time derivative of n naught plus n1 plus del dot n1 plus n naught u1 plus u naught is equals to 0. So, the time derivative of this is going to be 0, and if you use the basic principle that second order terms in perturbation variables are going to be neglected. So, if you do that, we can write the continuity equation dou n1 by dou t plus n naught del dot u1 is 0, right. So, similarly, we can use the perturbation for the momentum equation as well, and we can write the momentum equation as me n naught dou u1 by dou t is equals to minus e n naught e1 minus 3 kb te n1 and del n1. Right. And the Poisson equation as epsilon naught times del dot E1 is equals to minus E n. So, let us say we call this equation as equation number 7, 8 and 9. So, these are the linearized governing equations in which we have only the perturbation variables like modified velocity, electric field and the number density. Right. Now, the standard method is to assume sinusoidal variation of the perturbation variables. So, we will say that n1, the perturbed electron density, is n naught exponential I k x minus omega t. So, you are describing a sinusoidal variation in one dimension or along the x direction, or the electric field E1 as let us say E naught exponential I times kx minus omega t, and u1 the velocity as u naught exponential of I kx minus. So, we know very well only the real part will have some physical meaning when you take these solutions. So, we can use these set of solutions. Let us say we call them as equation number 10, and we have to use them using let us say set of equations in 10 in 7, 8 and 9. We will have to simply substitute them into this. So, for example, dou n1 by dou t would be n naught exponential I kx minus omega t times minus I omega, right. So, we take the derivatives as per these equations, and the gradient or the del operator is going to be only I cap dou by dou x, because we are considering a one dimensional picture, right. So, using this for the definition of del, and the other type of derivative is the time derivative, which is dou by dou t, or you can as well choose d by dx directly, because you are dealing only with one dimension. So, when you substitute these solutions into the linearized governing equations, what you will get is, you will get minus I omega n1 plus n naught I k u1 is equals to 0, which is from the continuity equation. You see this, the continuity equation, equation number 7 will give you this, and we call this as equation number 11, or we can, for simplicity, or if you want to call it, recall it easily, let us say we call it as A, and then I k epsilon naught E1 is equals to minus E n1. This is equation number B, and this is resulting from the Poisson equation. And the momentum equation, when linearized and upon substitution of the sinusoidal solutions, will be U1 minus I omega is equals to minus E n naught E1 minus 3 kBTE I k n1. Right. So, we have A, B and C. Right. Now, we have to eliminate some variables and obtain the dispersion relation, which is between omega versus k. So, if there is a wave in this picture, then the ratio of omega by k will give you the phase velocity, and the ratio of d omega by dk will give you the group velocity. So, from equation number B, from B we can write E1 as equal to minus E n1 divided by I k epsilon naught, right. Substituting this in equation number C, we will get m e n naught u1 minus I omega is equals to minus E n times minus E n1 divided by I k epsilon naught minus 3 kBTE I k n1. So, which will be minus I omega m e n naught u1 is equals to E square n naught by I k epsilon naught minus 3 kBTE I k times n1. Now, from equation number A, we can write n1. From equation number A, we can write n1 is equals to minus n naught I k u1 divided by minus I omega, which is equals to n naught k u1 by omega, right. So, we can use this n1 here. So, we have n1 written as n naught k u1 by omega. We can use n1 into this expression as this, right. Now, doing it, what we have is a simple algebra. I am doing it just so that we have continuity and you can understand it better. Minus I omega is equals to E square n naught divided by I k epsilon naught minus 3 kBTE Ik times N naught Ik U1 divided by I omega. We can cancel U1 which appears on both sides, and we can write ME N naught minus I omega is equals to E square N naught square K divided by Ik epsilon naught omega minus 3 kb TE I K square N naught divided by omega, right. So, we will take the omega on the denominator to the left hand side, and we will write minus I omega square is equals to E square N naught square K divided by I K epsilon naught times M E N naught. The N naught is the unperturbed electron density minus 3 kBTE Ik square N naught divided by Me N naught. So, omega square now becomes E square N naught square K divided by I K minus I square K epsilon naught times M E N naught minus 3 kBTE I K square N naught divided by minus I M E N naught. So, we will have this N naught all these things will be cancelled. So, omega square can now be written as E square N naught by Me epsilon naught plus 3 kBTE, this minus becomes plus kBTE K square divided by Me. This is an expression that we have got for omega in terms of K, the propagation constant. So, omega square is equals to E square N naught by Me epsilon naught plus 3 kBTE K square by Me. Now, if you consider the electron to have thermal energy or temperature, non-zero temperature, you can write half mv square is equals to kBT, right. So, what is this? This is the thermal energy. So, this is the kinetic energy, right. So, you can write V square is 2 kBT by M, or we call V thermal as square root of 2 kBT by M, right. So, this kBT by M can be written as V square by 2. kBT by M is V thermal energy square by 2, and this parameter E square N naught by Me epsilon naught is the plasma frequency. We call it as omega p, which is equals to square root of n naught E square by m E epsilon naught. So, we can substitute all of these things into the equation and we can rewrite as omega square is equals to, let us say we E square n naught by m E epsilon naught plus 3 kb T E times k square, the wave vector, by m E, right. So, omega square has to be rewritten as omega p square plus, so V T H square by 2 is kb T by m, kb T E by m or m E. So, kb T, this can be replaced, this part kb T E by m E as V T H square. So, it can be written as 3 by 2 V T H square and k square, right. So, this is the expression. This is the most important expression because it gives us a lot of information about the plasma wave. So, what is omega? Omega is the angular frequency of the wave passing through the plasma due to the electron oscillations. So, earlier we have realized electron oscillations do not propagate, they oscillate, and these oscillations do not constitute a wave or a wave train. What is a wave? A wave is something which carries information or energy from one point to another point. So, the plasma oscillations do not constitute a wave as long as you consider the plasma to be cold, but if you impose a condition that plasma particles or the electrons, if they have some thermal energy, these electrons, by the virtue of their thermal energy, will be transported from one layer to another layer. When they are being transported, you are actually conveying the message that they are actually taking some information from one layer to another layer of plasma. So, another layer of plasma knows, or the information is there about an earlier layer or a layer before that. So, there is an information passage from one point to another point. So, by considering the electron temperature to be non-zero, we have obtained a different expression for omega, and this expression seems to be a function of k. That means, Vg is, when you define Vg, d omega by dk is not equal to 0. What does it mean? This simply means, always just remember that wave propagation exists. Wave propagation simply exists, right. Now, let us look at the properties of this wave. So, omega square is the angular frequency of the wave is plasma frequency plus something, right. So, this is the plasma frequency. This is the plasma frequency, which is a characteristic of the plasma oscillation, and this part is because of the non-zero thermal velocity of electron, thermal velocity of electron, right. Now, let us try to rewrite this expression in terms of something that we know. So, we can define, we know very well, but that omega, let us say omega p e is square root of n e square by m e epsilon naught. V T H is 2 kb T E by m e, and if we recall the device length lambda d square as epsilon naught kb T by n naught e square. We can write this as, let us say, equation number 1 from here. Equation number 1 in terms of lambda d. How do we do it? So, omega, we consider the original expression, omega square is omega p e or electron plasma frequency plus 3 by 2 k square VTH square. So, we multiply and divide with something just to facilitate the inclusion of device length into this expression. So, 3 by 2 KB TE by ME times epsilon naught divided by epsilon naught times N naught E square by N naught E square. So, this one KBTE is a measure of the device length. So, we can write omega square is omega PE square plus 3 by 2 to k square. So, if I would write k square here to k square 2 lambda d square into N naught E square by ME epsilon naught. So, simplifying, omega square is omega PE square plus 3 k square lambda d square omega PE square. So, this is again the plasma frequency. How did we get this term? So, in order to accommodate lambda d, we multiplied with epsilon naught divided by epsilon naught, multiplied with N naught E square divided with N naught E square. So, just so that we can call this KBTE epsilon naught by N naught E square as lambda d square, and the remaining terms seems to be resembling the plasma frequency. So, the dispersion relation can now be written as omega square is omega PE square times 1 plus 3 k square lambda d square. This is another version of the dispersion relation of the electron plasma wave. So, this wave is called as the electron plasma wave. So, we have started from plasma oscillations. Which gave a situation Vg is equals to 0. The electron plasma wave, by assuming the temperature of electron not to be equal to 0, gave Vg as not equal to 0. That means, we can now call these oscillations to be responsible for a wave activity. Now, the task is to find out the phase velocity and group velocity, for which we can use this basic definition. So, we can write Vp is simply omega by k is, we can express it as Vth times omega divided by omega square minus omega Pe square. So, it is basically omega is square root of omega P square plus 3 by 2 k square Vth square divided by k. This is your Vp. So, I have rearranged the terms so that Vp can be written like this. What is this? This is the phase velocity. So, this velocity tells you how a given phase in the wave is propagating, or how it is moving actually, right. Now, when you calculate Vg, the group velocity, Vg is d omega by dk, which is equals to 3 by 2 k by omega Vth square. D omega by dk is, just take a derivative, you will get this, or Vg can be simplified to write it as 3 by 2 Vth square divided by Vp. The group velocity is 3 by 2 times the thermal velocity square divided by Vp. Right. So, this is something about the electron plasma wave, which is actually transporting energy from one point to another point. Now, if you want to understand more features about this dispersion relation, so like I said before, dispersion relation tells you all the required information about the plasma wave or any wave. So, we have omega square is equals to omega p square or omega p square plus 3 by 2 k square Vth square. So, in the next class, we will try to understand what is the graphical representation of this dispersion relation and what kind of emphasis can be drawn from the graphical representation.